cryptography in the last decade may apply to complex systems. Okay. So let's have a look more precisely to everything. So this is some kind of signal representation of the internet. As you see, drawing a graph is a challenge. Okay, it's at least it's beautiful. It looks like a Christmas tree exploding, but I don't know if we can tell anything about from these pictures. It's I'm not really convinced. So you have billions of nodes at edge, okay, and this is a huge problem. This is a huge problem because it's hard to draw, okay, it's hard to get the pictures, for instance, so you have to find some nice algorithm. You cannot do it by hand, okay, you have to design automatic procedures that will do it, okay, and automatic procedures are algorithms. And these are quite challenging because since you have a billion of nodes, you're not allowed to have an n-square algorithm, for instance, because it will last forever. I mean, forever. So you need at most a linear algorithm. Better if you can do a sublinear algorithm, and even better if you can fit it in your laptop. I mean, if with a very small memory, it's even better. Okay. So, for instance, computing the diameter of this graph is a real challenge. Okay? Nobody has an algorithm that can do it. Okay, finding the 2 points that are the furthest away into the giant connected components of this graph, it's a real challenge. No trivial algorithm will do it. You have to design specific algorithms. So there is a huge part of computer science now working on trying to construct algorithms, okay, that are efficient on huge graphs, and trying to understand how to draw them and especially do it efficiently. Okay, so this is really computer scientist stuff. I mean, this is useful for others, but it's really a technical part. I mean, these are for computer scientists. And also, you need also specific algorithm to represent the data. But not only, you need also specific algorithm to extract the data. Okay? For instance, Amazon collects a huge number of information on you. Where do you go? What do you look? Whether you buy it? What do you buy after having looked at these items and everything? Okay, you know that because they display it. Okay, they display it to you. They tells you that after watching this item, they finally 60% of the people end up buying that stuff and everything. Okay, so how do they extract this information? This is not really not a trivial task. Okay, especially the recommendation of Amazon is pretty amazing. That means that they get some kind of profile of you, and then they tell you, okay, you should buy that, and often it works. Okay, this is the same thing for AdSense by Google. Okay, and behind that there are a lot of algorithms. And for instance, the way the recommendation of Amazon works is a very nice algorithm, which is the following: is that the problem that you have is that you have a huge matrix. Here you have the clients, okay, and here you have the items, okay, and you know that this client bought this item at some point, okay. But this matrix is definitely too huge. It won't fit in any computer, and it will not tell you anything interesting. Okay, you will just know that this client bought this item, and how will I do a recommendation from that? So what they did is simply approximate this huge matrix A by a k-rank matrix, a matrix of rank k. Okay, and it's any k-rank matrix A prime can be written something like R times V, where it's a k by n matrix and k by n matrix. Okay, so it's much smaller. Okay, here you had an n times m matrix, and where m is the number of items and n is the number of clients. And here you can fix a k, and then you have something which is k times n plus m instead. Okay, which is quite small. It's square root of it, more or less. Okay, even if, especially if k is about 10, for instance. Okay, and then you get a much smaller representation of the matrix, and furthermore, what you get is a much smaller, a much better estimation for recommendation. Because basically what it does is that this algorithm, you can show it, is that it clusters the things. That means that if you have a lot of clients, okay, but a small number of profiles, okay, a small number of type of clients, I mean, people which are interested more in music and less in sports or things like that. You don't have that much possibilities, okay? Then this process will properly cluster the things. And then you will be able, from this process, to tell that to tell in which group is which person. Okay, so this is known as latent semantic intuition or whatsoever. And this algorithm is typically the key for the Amazon recommendation system. So clearly, you see that it has nothing to do with it's math, basically. And this is the way it works. So this is the way you deal with large networks. You have to think about it as a matrix or whatsoever, and try to come up with nice algorithms to understand. Okay. For instance, the Google rank algorithm also. You know that Google, there are 2 points in Google. First, it's very fast. Tells you very fast what kind of page you want. And second, the order is quite reasonable. If you look at the first 10 items, they are quite relevant. Okay? And this is because of algorithms, specific algorithms that were developed. Okay? So that's the kind of things where computer scientists work on. So you have also mathematical tools. So for instance, you know that physicists and so by computer scientists in the large sense, okay, there are a lot of interactions between theoretical physics and computer science. And so for instance, the problem is that when you want to do simulation, you want to generate random stuff. Okay, you need random things. Okay, so we've seen before that it's not that hard. It's not really easy to generate random sequences. Okay, but if you want to generate something which is not a uniform sequence of 0 and 1s, okay, but for instance that a tiling. Okay, so this is a uniform tiling of this shape. So you have this shape. So I don't know if you know what the tiling is. It's simply, so in that case you have a shape here, which is over a triangular lattice. Okay, and you want to tile it with lozenges. So you have this one, and this one. Okay, and you want to study that. What is why is it interesting? It's because basically, if you want to look at catalyzers, and you imagine that these are diatoms that are placed over a catalyzer. Okay, so imagine that you have a triangular grid here. Imagine that your atoms are placed over a triangular grid. Okay, and you have diatoms that are placed here. Okay, so for instance, you have another one here, and you have another one. So triangular lattice. Okay, you have another one there. Okay, on the triangular lattice, you have three possibilities to place yourself. Okay, and you have boundaries. Okay, and you want to understand how diatoms place themselves over the catalyzer. Okay, and for instance, if you have a specific shape for your catalyzer, what you discover is that there are places where everything is fixed. I mean that the diatoms have to be placed in such a way else you won't cover everything. Okay, so this is the typical things, and generating these kind of figures is not that easy. Okay, I mean, you need to think about algorithms to find a way to generate them efficiently, because usually you don't want to run one simulation, you want to run a lot of simulation. Okay, if you want to compute the average energy of such a configuration or whatever, you need to generate a lot of these samples. Okay, and generating these samples requires quite sophisticated algorithms. Okay, as you may see here, there's a cardioid here. There's a cardioid, but outside the cardioid everything is fixed. Inside it's random. And another example of what graph theory can do, okay, because graph theory and combinatorial algorithm is, for instance, telling whether a molecule is stable or not. So this is quite funny. It's that the food baleine, okay, this molecule, which looks like a football, okay, football ball, or soccer ball, was known to be stable before it was realized. Okay, it was proved to be stable before they tried to make it. Okay, and how did they prove it was stable? So this is a kind of molecule which are